Your private messages are not protected by a complex lock, but by a simple arithmetic trick. While computers are incredibly fast at calculation, they are fundamentally broken when asked to reverse one specific operation. Think of it like a physical trapdoor. It is trivial to fall through, but nearly impossible to climb back up. In mathematics, we call this an asymmetric function, where the cost of reversing is astronomical. Everything starts with two massive prime numbers, which we keep absolutely secret. These primes are the seeds of our security, and finding them requires testing thousands of random digits for primality before proceeding further. We multiply these two secret primes together to create a massive public number called the modulus. This value is shared with the entire world, and it defines the boundaries of our mathematical playground during encryption. An attacker sees the public modulus and knows it is a product of two primes, but they cannot find which ones. The difficulty of factoring this giant number is the only thing stopping them. To build the keys, we first calculate a hidden value called the totient. This number represents how many smaller integers do not share any factors with our public modulus, excluding the number itself. Calculating the totient is easy if you know the secret primes, but impossible if you do not. This secret knowledge is what allows the key owner to create a matching pair for the lock. Next, we choose a public exponent, often a small prime like 65,537. This number is combined with the modulus to form the public key that everyone can see. We must ensure that our chosen exponent does not share any factors with the totient. This mathematical alignment is required to ensure that a unique inverse exists, allowing us to eventually undo the encryption. The private key is calculated using the extended Euclidean algorithm to find a specific number. This value, when multiplied by our public exponent, leaves a remainder of 1 when divided by the hidden totient. All RSA operations happen within modular arithmetic, which works like a clock. Instead of numbers growing infinitely large, they wrap around a fixed limit, keeping the results within a predictable and manageable range. To hide a message, we treat it as a number and raise it to the power of the public exponent. We then take the remainder after dividing by the modulus to produce the ciphertext. The resulting value looks like random noise. Without the private key, there is no known way to reverse this power operation efficiently, even if you know exactly how the encryption was performed initially. To recover the original message, we take the ciphertext and raise it to the power of the secret private exponent. After applying the same modular division, the original number magically reappears for us. This works because of a deep property of modular powers. Raising a number to one power and then another effectively cancels out, provided the exponents were chosen according to our secret totient rules. The underlying proof relies on Euler's theorem, which links prime factorization to modular cycles. It guarantees that our two-step process will always return the starting value, ensuring no data is lost or corrupted. An attacker must factor the modulus to find the secret totient and recreate the private key. For a 2,000-bit number, this would take trillions of years using every computer currently existing on Earth. While brute force is impossible, researchers look for clever shortcuts in the math. So far, the gap between multiplying and factoring remains wide enough to protect nearly every transaction and secret on the internet. RSA is a testament to the power of pure mathematics in the physical world. By turning a simple numerical hard problem into a digital shield, we have built a foundation for global trust.